Hello. In this paper, my supervisor Danny Silva and I did a comparison of two algorithms, convolutional neural network and deep belief network, to limit their performance with two experiments. In this presentation, I will quickly introduce CNN and DBN, declare our theory, show two experiments and the results, then bring out the conclusion. We cannot trust what the user will input to a computer program when we start to use classification algorithms in daily life and do important jobs. Therefore, we need to assume that the classification algorithm may receive input that is designed to have the AI fail to do its job. The primary undertaking in this research is to compare self-supervised methods such as DBNs to contemporary human-engineered machine learning methods such as CNN on classification problems that suffer from adversarial attacks. For those who are not familiar with standard machine learning algorithm, CNN is a feed-forward neural network with excellent performance on image classification, object detection, tracking, and counting. CNN uses kernels to scan and pass to next layer, and this will be the key difference compared to the other algorithm. This will cause the convolution assumption that pixels proximal to each other are related. It's an inductive bias that normally provides an advantage for image classification and regression. Deep belief networks are structured autoencoders. A DBN can be constructed of multiple restricted Boltzmann machines and can be fine-tuned for classification using gradient descent and backpropagation algorithms after adding a fully connected layer at the top. There is no specific bias because there is no kernel used to pass information. In previous research, people had discovered adversarial attack. This method changes every pixel a little bit, and the neural network will fail to identify the object. Another method is called one-pixel attack, which only changes few pixels to fool the neural network. Their purpose is to reduce the accuracy of top-tier algorithms as much as possible. Our theory is that CNN makes a strong inductive bias assumption about the relationship between pixels that are proximal to each other, and this will be a disadvantage for CNN when people intentionally modify the pixels. We wish to show that the CNN inductive bias, according to proximity of pixels, which assumes pixels adjacent to each other will tend to have the same color and brightness, fails under certain adversarial attacks. DBN, which learn features with a less specific inductive bias with no assumption about the proximity of pixels, will not fail in the same way. So we set up architectures that have similar complexity for both algorithms, which means when we multiply and add up the nodes connecting between layers, they end up to very similar result. We implemented two experiments, and I will now present their general analysis how both algorithms perform on common correct and common mistakes. So first, we scrambled all of the pixels of each picture in a consistent manner. Then we tested how CNN, DBN, and AN perform when training and testing with mixed pictures. The purpose is to show CNN will lose to DBN when advantages gained from relationship between pixels, which is kernel, no longer exist. And we set up a standard AN, which is an exact same copy from my DBN code, but got replaced the pre-training part with random generated weights. The purpose is to show that the unlabeled data gains advantage for self-supervised learning methods, since it is more realistic to have them in real life. We recorded how each algorithm performs before and after attack. The pictures showed the average performance over multiple rounds of CN, DBN, and AN on MNIST dataset before and after mixing up the pixels of the image. The left picture shows that CN and DBN performs as expected before the attack. The right picture clearly shows the mixing of the pixels reduced the accuracy of both CN and DBN, and when pixels were scrambled, the accuracy from these rounds of DBN and CN has a statistical difference in favor of DBN. It is worth to noting that for 150 training examples, t-test values are smaller than 0.05, which means there are statistical difference between the accuracy of two models in favor of DBN. Another interesting fact is that the confidence of CN to train and test on mixed pictures is very high, which is not expected. The standard AN results showed that the RBM pre-training is an important aspect of DBN models. The pre-training examples are unlabeled data which do not come with the cost of labeling each image. In the second experiment, our purpose is to iterate the black dot from the first pixel to the last. If the model failed to label the picture at any position, the attack is considered success. The expected result is that CN will be affected more than the DBN. This will demonstrate that the CN is too dependent on the pixel in subfeature, and this assumption has now become a disadvantage. The neural networks are trained before the attack and tested after the attack. The left picture compares the CN and DBN performance on the CIFAR-10 dataset before and after attack. CN models correctly classified about 5,700 images on the average out of 10,000 of normal images. It then misclassified a lot of them after one pixel attack, with remaining about 4,200 correctly classified. This shows that 26.1% of the attacked image were misclassified. The DBN models correctly classify a little bit less than CN before the attack. It then misclassified only 293 of these under one pixel attack, or only 6.3%, and takes the lead. The right picture shows the common correct examples before the attack. Is about 1/3 for both algorithms. DBN still have most of them correct after the attack, with only 4.78% error, while CN made a lot of mistakes after the attack, which is 18.77% error, which is about 4 times DBN's error. These two pictures show how CN and DBN model perform under attack on examples that the other algorithm did not correctly identify before the attack. This shows that for 1,016 examples that CN uniquely misclassified before the attack, that DBN correctly classified 896 of these after the attack, which is 88.19%, whereas about 2,000 examples that DBN uniquely misclassified before the attack, CN correctly classified only about 1,200 of these after the attack, or just 61.08%. In summary, the CN algorithm, by using convolutional kernels, makes a strong inductive bias assumption about how pixels are proximal to each other can develop internal representation crucial to learning. However, our experiment showed that the same bias can be a significant weakness that makes CN models vulnerable to adversarial attacks. In comparison, the DBN algorithm assumes that the best internal representation can be developed by pre-training the network using large set of unlabeled examples from same input space without other a priori assumptions. CN's inductive bias becomes a disadvantage when the assumption of the relationship between proximal pixels no longer holds. The DBN models also demonstrate that semi-supervised learning methods take advantage of freely available unlabeled data and do not need large quantities of labeled examples as compared to strictly supervised approach. This suggests that in the context of lifelong machine learning system, that the DBN approach of learning the underlying internal representation is superior to the highly engineered CNN approach. In this research, DBN had a lower initial accuracy with large training set compared to DBN. This paper did not find a better accuracy. I think that if CNN can do better than humans, DBN can do it as well, but maybe on another application scenario or more complex architecture. A logical next step for this research is to use more complex real-world examples to test how each algorithm performs. Some advanced attack method introduced in the background section in adversarial attack area has been published and has not been tried in this research because of the time limit. An analysis of hidden layer weights of activation will be a valuable area to study. By showing the details inside the hidden layers, we can analyze why some attacks cause the CNN to fail and DBN to succeed. This paper only focused on image classification. Many domains like object tracking, voice detection or analysis, text analyzing, and anything related to problems with local correlation could also be used in future studies. Thank you for your listening.